Hey there, and welcome back. We're diving into deep learning today, specifically, this research you sent over on this new type of transformer called KT.
Now, I know Kolmogorov-Arnold Transformer might sound, well, a tad intimidating.
Yeah, sure.
But trust me, way cooler than it sounds, and we're going to break it down. And by the end of this deep dive, you'll be able to impress all your friends with your AI knowledge.
I have faith in you both.
So to really understand why Kate is such a big deal, we need to start with transformers themselves.
I mean, these things are everywhere in AI now, right?
Absolutely, yeah. They've really become the backbone of a lot of modern AI.
From language processing to image recognition.
Okay, but before we get too far, can we do a quick jargon-free refresher on what a transformer actually is?
Sure thing. Imagine you're trying to understand a sentence.
You don't just process each word in isolation, right?
Right.
You pay attention to how each word relates to the others.
The context.
Transformers do something similar with data. They're able to weigh the importance of different parts of the input, which makes them really good at understanding relationships and patterns.
Right. It's like they have that built-in sense of context.
That we use so naturally.
Exactly.
That makes sense.
So where do these MLP things, the multi-layer perceptrons, fit into all of this? They sound kind of important.
They are, yeah. MLPs are like the engines within traditional transformers.
They're neural networks that process and transform information flowing through the model.
Think of them as the gears that make everything work.
Okay, so if MLPs are the engines, what's the problem? Why the need for this whole KT thing?
Well, like any engine, MLPs have their limits.
They're great for a lot of tasks, but they can get bogged down when dealing with super complex functions or patterns in the data.
So it's like trying to run a high-powered sports car on, like, regular fuel. It might work, but you're not getting the full potential.
Exactly. And that's where CANs, or Kolmogorov-Arnold networks, come in.
They're like switching to that high-octane fuel.
KANs, now those sound even more complex than transformers.
They might sound intimidating, but the core idea is actually pretty elegant.
See, KANs are based on this mathematical theorem called the Kolmogorov-Arnold representation theorem.
Okay.
Don't worry, you don't need to memorize that.
But what it basically says is that any continuous function, no matter how complex, can be represented by combining simpler functions.
Okay, so instead of trying to model some super complicated relationship all at once,
Yeah.
KANs break it down into smaller, more manageable chunks.
You got it.
And the theory is that this makes them much more efficient.
Okay.
KANs could potentially use fewer parameters, which are like the knobs and dials a neural network uses to learn, while still being able to model those really complex relationships and data.
It's like having a more powerful engine that's also more fuel efficient.
Okay, that's pretty cool. So why aren't we seeing CANs everywhere already? What's the catch? There's always a catch, right?
You're right. There's always a catch.
And in the case of CANs, there are a few.
3 main challenges, to be exact, that have held them back. And these challenges are exactly what the researchers behind KT were trying to overcome.
Okay, I'm intrigued. Let's unpack those challenges. What's the first hurdle?
The first hurdle has to do with the base function traditionally used in cadence.
Something called a B-spline?
B-splines. Okay, for those of us who haven't taken a deep dive into advanced math lately, what are we talking about here? And why are they a problem for AI?
So B-splines are essentially mathematical curves used to create smooth shapes.
They're great for a lot of things, but they're not very GPU friendly.
Hold on, GPUs, those are the things that make video games look amazing, right? What do they have to do with AI?
They're essential for deep learning. See, GPUs are designed for parallel processing.
Meaning they can handle tons of calculations at the same time.
This makes them perfect for training and running large AI models.
So it's like trying to run a complex simulation on a calculator instead of a supercomputer. It's just not going to be pretty.
Exactly. And that's the problem with B-splines.
They're computationally expensive, which slows down training and limits the size of models that can be practically used.
Okay, so that's one challenge down.
What's the next hurdle TANs need to clear?
The second challenge is that CANs can be, well, computationally demanding.
In terms of the sheer number of parameters they require.
Okay, so remind me again, parameters, those are like the internal settings the model tweaks as it learns, right?
Yeah.
What's the issue with having a lot of them?
You got it.
In a traditional CAN, each connection between inputs and outputs needs its own set of parameters.
Its own little function to figure out how information should flow.
As the network grows, the number of these connections explodes.
Okay.
And so do the parameters.
It's like having a giant library with millions of books, but no real organization system.
Yeah.
It becomes a computational nightmare to manage all that information.
So it's not just about the speed of each calculation,
Right.
but also the sheer volume of calculations that need to happen. Sounds like a recipe for AI gridlock. Now, the third challenge, and this is a big one for any deep learning model,
Is weight initialization.
weight initialization. That sounds familiar.
It's about finding the right starting point for the model to learn effectively right.
You got it.
It's like trying to climb Mount Everest.
You don't want to start at the bottom of the ocean.
Right.
You want a base camp that gives you a fighting chance.
With Karens, because they have these flexible, learnable activation functions, finding the right starting point for all those parameters is even more crucial.
Get it wrong, and the whole learning process can become unstable.
So to sum it up, KNNs have the potential to be super powerful and efficient, but they've got these three big hurdles to overcome. The GPU incompatibility of B-splines, the parameter explosion, and the tricky weight initialization.
Right.
It's like they've got all the ingredients for an amazing meal, but no one can figure out the right recipe to put it all together.
That's a great analogy, but that's where KK comes in.
Okay.
The researchers behind KT looked at these challenges and saw an opportunity to reimagine how KNs could work.
Okay, let's talk about KT. How does it address these challenges? Does it manage to cook up that amazing AI meal?
It does. Remember those three challenges we discussed?
Yeah.
KT tackles each one head on.
All right, challenge number one was the B-splines and their incompatibility with GPUs.
Right.
What did the KT creators do about that?
They ditched the B-splines entirely. Instead, they introduced something called rational functions.
Rational functions. Okay, without going full math whiz on us, what are they and why are they better than B-splines in this context?
In simple terms, rational functions are just mathematical expressions that involve dividing one polynomial by another.
What makes them so great for KT is that they're much more GPU friendly.
GPUs can process them way faster than B-splines.
So it's like swapping out those clunky old engine parts for something specifically designed for high performance.
Exactly.
And here's the kicker. Not only are rational functions faster, but they also have some theoretical advantages.
Okay.
They can be incredibly flexible in approximating complex relationships, potentially even more so than B-splines.
So it's not just a quick fix.
It's a fundamental improvement that could unlock even more potential down the line. That's impressive. Okay, what about that second challenge, the parameter explosion? How did KT tackle that beast?
For that, they developed an ingenious technique called group can.
Group can, it sounds like some sort of exclusive AI club.
Well, it's exclusive in the sense that only KT gets to use it. Here's how it works.
Yeah.
Remember how we talked about each connection in a traditional can needing its own set of parameters?
Yeah, it's like that disorganized library.
Exactly.
Well, group can allows groups of connections to share the same set of parameters.
It's the same function.
It's like organizing that library, putting all the books on similar topics together.
This dramatically reduces the number of parameters needed without sacrificing the model's ability to learn complex patterns.
So it's like KT is finding elegance and efficiency by recognizing that sometimes sharing is caring. It's not always about having more, but about using what you have more effectively.
Yeah.
Clever.
It is clever.
Yeah.
And it's paying off.
Now, the third challenge, remember weight initialization.
Yeah, finding that Goldilocks zone for the model to start learning effectively.
Right.
What did KT do there?
They implemented something called variance-preserving initialization.
Variance preserving. Okay, break that down for me. What's the key insight here?
Think of it like this. You're trying to train a dog.
If you start with commands that are way too complex.
Or rewards that are inconsistent, the dog's going to get confused and frustrated.
Right. You've got to find that sweet spot, clear, consistent guidance that makes sense to the learner.
Exactly.
Variance preserving initialization is like finding that sweet spot for KT's parameters.
It ensures that the initial values of those parameters are set in a way that keeps the learning process stable and efficient. No confused AI puppies here.
Okay, so KT has addressed all three challenges. It's got the speed of rational functions, the efficiency of group can, and the stability of variance-preserving initialization. That's a powerful combination. But the real question is, does it actually work? What kind of results is KT seeing out in the wild?
That's what you really want to know, right?
Yeah.
Well, get ready to be impressed because KT isn't just theoretically sound.
It's delivering some seriously impressive results in practice.
Okay, let's hear it. What has KT accomplished so far? Give me the highlights. Okay, so we've covered how KT works, but I'm dying to know, what does this all mean in practice? How is KT actually being used?
Well, one of the most impressive things is how KT's performing on image recognition tasks, we're talking consistently outperforming standard transformer.
And not just by a small margin either.
Image recognition, that's huge. I mean, that's everything from self-driving cars being able to see better to medical AI making more accurate diagnoses from scans.
You're getting it. The applications are mind-blowing.
And the numbers speak for themselves.
Okay.
For example, one variant, KATB, scored a whopping 82.3% accuracy on the ImageNet 1K benchmark.
82.3%. Whoa. That sounds crazy high.
How does that compare to the standard transformers it's up against?
It's a significant leap. We're talking a solid 3.1% better than a standard transformer of a comparable size.
And in the world of AI, where even tiny gains are celebrated, that's a big deal.
Okay, so it's a clear winner in terms of accuracy. What about speed? We talked about those rational functions making it theoretically faster.
Right.
But does that actually pan out in real-world scenarios?
That's the really exciting part. They tested KT by initializing it with pre-trained weights from a standard transformer.
Essentially, they gave it a head start using knowledge already learned by another model.
So like giving a student a textbook before a big exam.
Exactly.
And the results were even better. They saw even higher accuracy with those pre-trained weights.
It's like KT took that head start and just ran with it, learning even faster and more effectively.
That's incredible. So we've got accuracy, we've got speed, anything else KT can do.
It's not just a one-trick pony. KT also shows real promise in other vision-related tasks.
Things like object detection, being able to pinpoint exactly where objects are within an image.
And semantic segmentation, understanding what different parts of an image represent.
So not just identifying a cat in the picture, but knowing exactly where the cat is, that it's sitting on a mat, and that the mat is next to a door.
Exactly.
And that kind of fine-grained understanding opens up even more possibilities.
Imagine AI systems that can generate realistic images and videos, robots that can navigate complex environments, all thanks to Kate's ability to see the world with such detail and nuance.
This is seriously cool stuff.
Yeah.
But every time I get excited about a new technology, I hear that little voice in the back of my head whispering, okay, but what's the catch?
Sure.
There've got to be some challenges still facing KT, right?
You're right. There are always challenges.
For example, while those rational functions are a big improvement, KT's overall processing speed still lags behind some simpler approaches. It's like having a super efficient engine.
Yeah.
It might get great mileage, but it might not be the fastest car on the track.
So a trade-off between speed and efficiency, what other hurdles are there?
Well, those rational functions, while powerful, can be a bit tricky to work with.
There are some stability issues that can pop up, and the backpropagation process, that's how the model adjusts its learning based on feedback, can get a bit more complex. Like having a powerful tool, you need to learn how to handle it properly to get the best results.
Makes sense. So fine-tuning and optimization are still crucial.
Right.
What about scaling this up? Kate seems amazing in a research setting, but can it handle the really big leagues? Real-world applications with massive data sets?
That's the million-dollar question. Scaling up is a challenge for any AI model.
And KT's no exception. Right now, it's showing incredible promise.
But deploying it for something like processing an entire language or controlling a fleet of robots, that will take more breakthroughs and refinements.
So lots of potential, but still some growing pains to overcome. That seems to be a recurring theme in the world of cutting-edge AI, doesn't it?
It absolutely does.
But that's the beauty of research and development.
Each hurdle overcome, each challenge addressed, brings us one step closer to realizing the full potential of these technologies.
I like that, a spirit of continuous improvement. So for someone like me, or anyone listening who's trying to keep up with this ever-evolving AI landscape, what's the key takeaway from our KT Deep Dive? What's the one thing you really want them to remember?
Remember this, KT is a testament to the power of ingenuity in AI research.
It shows how we can take theoretical concepts and, with some clever engineering and a lot of hard work, turn them into reality. This is a field that's constantly pushing boundaries, and KT is just one example of the amazing things that are possible when we combine innovative thinking with rigorous experimentation.
I love that. So it's not just about what KT can do today, but about what it represents for the future of AI.
Right.
More powerful, more efficient, and constantly evolving.
Precisely.
Well, I've definitely had my aha moments during this deep dive. Thank you so much for breaking down this complex topic in a way that even I could understand.
My pleasure. It's always exciting to talk about breakthroughs like this.
And to all of you listening, thanks for joining us on this deep dive into the fascinating world of KP and deep learning.
Keep those questions coming, and we'll catch you on the next deep dive.